In the last class we have seen the concept of isoparametric mapping, using which we can express the physical coordinates x, y in terms of parent coordinates, parent element coordinates s and t, using shape functions of parent element and the spatial coordinates of the physical element. So basically isoparametric mapping is a relation which relates physical coordinates of elements with the coordinates of parent element. And after that we looked at how to calculate derivatives of shape functions with respect to the physical coordinates x, y if the shape functions of derivatives with respect to the parent element coordinates s and t are known. For that we require what is called Jacobian. So Jacobian matrix is the one which relates the derivatives of shape functions in the physical element coordinates x, y with parent element coordinates s and t. And to get the inverse relation, that is if we know the derivatives of shape functions with respect to the parent element, how to get the shape functions with respect to the physical coordinates, how to get shape function derivatives with respect to the physical coordinates x, y, we require determinant of Jacobian. And in the last class we have seen for a valid mapping determinant of Jacobian should be greater than 0, because if determinant of Jacobian is not, or if determinant of Jacobian is equal to 0, then there is that relation, that is we cannot calculate derivatives of shape function with respect to the physical coordinates if we know shape function derivatives with respect to the parent element coordinates s and t. So we took two types of elements, 4 noded quadrilateral element and 8 noded quadrilateral element, and we checked for isoparametric mapping validity by plotting determinant of Jacobian as a function of s and t. And also we plotted the other way of checking is we can also plot the physical coordinates x, y in terms of s and t, and see if there is any if it produces the shape of actual element or not. And if one plots determinant of j needs to be checked whether it is greater than 0 over the entire parent element domain. So this is how we can check the validity of isoparametric mapping. And after going through 4 examples, what we can make some conclusions out of what we studied in the last class. So that is why we will be looking at proper modeling with isoparametric element in this lecture. So from the above examples, here above examples means the examples that the 4 examples that we looked at in the last class, it is clear that there must be some restrictions on placement of mid-side nodes. For one dimensional quadratic elements it is possible to show mathematically that determinant of j will not attain 0 if mid-side node is placed in the middle half of the element. That is what basically we did when we looked at one dimensional quadratic element. And what we derived, or what we the result that we got for one dimensional case is reproduced here. If you have an edge which is of length L, then the two, excluding the two extreme nodes, extreme end nodes, the mid-side node, the location of it should be between L over 4 and 3L over 4, where S is measured from one of the ends of one of the extreme nodes, and L is the total length of that side. So this is the requirement if determinant of j is should not be equal to 0. So, same thing we can extend for 2 dimensional case. So, the placement of mid side node should satisfy this condition, S should be between L over 4 and 3 L over 4, and it is difficult to derive such a condition for 2 dimensional problems. However, if 1 dimensional condition is followed along each side of element, mapping is usually satisfactory. So, there is nothing special with respect to 2 dimensional element. Whatever condition we derived for 1 dimensional element, that we need to check for each of the sides of a 2 dimensional element for mapping to be satisfactory. And if you recall, in yesterday's lecture, we have taken the last example that we have taken is an 8 noded element, where node 1 node 2 is placed very close to one of the nodes, node 3, and there we have seen some problem with determinant of j being not greater than 0. So, because that happened because it violated this condition that the placement of mid side node is not satisfying the condition that it should be between L over 4 and 3 L over 4 for that particular example. The mapping problems may also arise when Jacobian matrix is nearly singular due to round off errors or due to badly shaped elements. So, these are the two reasons why Jacobian matrix may be nearly singular, that is almost singular. Round off errors may be controlled by using higher precision during calculations, and also changing units in which problem is defined, or using some other suitable technique. So, this is how round off errors can be controlled. And what about badly shaped elements? We have looked at, if you recall, in the last class we have seen a 4 noded element, which is second example under validity checking of isoparametric mapping. There we have taken an element intentionally which is very bad shaped element, and there the mapping turned out to be bad. So, to avoid problems due to badly shaped elements, it is recommended that the inside angles in quadrilateral element be greater than 15 degrees and less than 165 degrees. If we have violations of this inside angles, then we may have mapping problems similar to what we observed in the last class. So, the two requirements are: the mid side node should be positioned such a way that it is between L over 4 and 3 L over 4 of a particular side, and the angle between or the inside angles in a quadrilateral element should be greater than 15 degrees and less than 165 degrees. The following example demonstrates disastrous results due to a common input error while using finite element analysis computer programs. Sometimes the node numbering, if we do not follow, if we violate that, either for 2 dimensional case either all the nodes should be numbered in clockwise direction or anti-clockwise direction, sometimes some problem with results may arise. And if a program expects element connectivity to be defined in a counterclockwise manner and user enters a data as shown in figure below, mapping will obviously fail. So, the computer program is expecting the node numbering should be given in a particular direction, that is here counterclockwise manner, but user input data is not according to that requirement. So, then mapping is going to fail. To demonstrate that, an example is given here. Actually it is a 4 noded quadrilateral elements, but taking in counterclockwise direction, the node numbering should be 1, 2 and after that 3, 4, but here if you see the node numbering is one, 2 and 4 and 3 if we take in the counterclockwise direction. So, the computer program when it reads, it takes the nodal connectivity as 1, 2, 4, 3 instead of 1, 2, 3, 4. So, what happens? Most commercial codes checks for 0 Jacobian condition and warn user if Jacobian matrix is singular, but this checking business that this commercial software is going to do is only at a few selected points. However, a user must still be careful in following program input instructions, because 0 Jacobian is usually performed at few selected points. So, what is going to happen? It is possible to have non-zero Jacobian at those points where commercial software is checking, but overall mapping may still be invalid. So, now let us look at this example. What happens if the commercial software or if a particular software expects the nodal information be given in a particular direction, but if user inputs in a different way, what is going to happen? So, let us take that example. So, nodes are numbered 1, 2, 3, 4. Instead they should have been numbered as 1, 2, 4, 3, or the nodal connectivity should have been 1, 2, 4, 3 instead of 1, 2, 3, 4. So, let us see what is going to happen, and let us note down what are the physical coordinates x1 to x4 from the information that is given from the problem, and y1 to y4. After this element is, we are going to map it onto a 4 node parent element. So, taking parent element shape functions, we can write isoparametric mapping expressions, that is x in terms of s and t, y in terms of s and t, using parent element shape functions and physical element coordinates. Isoparametric mapping, once we do that, we get these relations between x and s and t, y and s and t. Using that, by taking partial derivatives of x with respect to s and t, y with respect to s and t, we can easily calculate determinant of j, which is given there. And let us check where this determinant of j, along what line this determinant of j is going to be 0. Equating determinant of j to 0, we get determinant of j to be 0 along the line which satisfies the condition s plus 6t is equal to minus 1. And as I mentioned in the last class, if you plot this line, if you overlay this line, that is s plus 6t is equal to minus 1 on the parent element domain, which goes s going from minus 1 to 1, t going from minus 1 to 1. If you overlay this line on that, it can be clearly seen that this line is going to cut across the domain. So, mapping is not going to be good, mapping is not good, because this line is going to cut across the parent element domain. The other way of checking the same thing, whether the mapping is valid or not, is plotting x y as a function of s and t, and here it can be clearly seen there is a fold which indicates mapping is not good. Element plot clearly demonstrates that element is not properly or not mapped properly. If mapping was good, then we are not going to have this kind of fold, and whatever the shape that we are going to get exactly looks like the physical or the actual element that we started out with. So, placement of nodes and the internal angles of a quadrilateral, these two requirements are very important for mapping to be good, isoparametric mapping to be good. And whatever we have studied for 2 dimensional elements can easily be extended for 3 dimensional elements as well. And now let us look at numerical integration for quadrilateral elements, because the matrices and vectors that we are going to get for quadrilateral elements, the integrand for the integrals is not going to be a constant like in 3 node triangular element, which is linear, but they are going to be function of x and y, or in turn function of s and t. So, when we are performing numerical integration, or when we are trying to evaluate these integrals, we need to adopt numerical integration, because we may not be able to find the closed form expressions of these so easily, because the integrand becomes complicated. So, now let us look at numerical integration for quadrilateral elements. The Gaussian integration formulas presented earlier for 1 dimensional integration can be extended to 2 dimensional integration over a square. Here basically whatever quadrilateral element or rectangular element we have, we are going to map it onto a parent element where s goes from -1 to 1, t goes from -1 to 1. So, we need to understand how to do a Gaussian integration over a square or a parent element going with s going from -1 to 1, t going from -1 to 1. So, the integration formulas presented for 1 dimensional integration, now they will be extended for 2 dimensional integration over this parent element. These formulas are also called product Gauss integration formulas, and basically this is how we will be evaluating. In 2 dimensional case, I is equal to -1 integral -1 to 1 double integral -1 to 1 -1 to 1 f as a function of s and t ds dt. So, let us say, suppose that is the function we need to evaluate, that is numerically approximated as double summation I going from 1 to m, j going from 1 to n, weight in the s direction times weight in the t direction, that is wi times wj times function evaluated at each of these integration points, that is I going from 1 to m, j going from 1 to n, that results in a grid. So, at each point of this grid we need to evaluate this function and multiply with corresponding weight, which is going to be wi times wj, and sum it up, we are going to get approximate or approximation of the integral I. So, here Si and Tj are Gauss point locations, m number of Gauss points in s direction, n number of Gauss points in the t direction, and wi, wj are the weights, Gauss weights in s and t directions. Function Si Tj is the value of integrand at the point Si Tj, and total number of Gauss points, there are m number of Gauss points in the s direction, n number of Gauss points in the t direction. So, total number of Gauss points is going to be m times n, and the location of Gauss points in each direction and corresponding weights are same as those which we already looked at when we are looking at one dimensional integration, one dimensional Gaussian integration. So, for completeness they are repeated here, and before that we will see few commonly used integrations for two dimensional case. Here one by one integration is shown, that is along s direction one point is taken, and again along t direction also one point is taken. So, that results in one by one integration, and 2 by t integration, 2 points are taken, 2 Gauss points are taken in s in the direction of s, and 2 Gauss points are taken in the direction of t. So, it results in total 2 by 2, which is going to be 4 integration points. Similarly, 3 by 3 integration, where 3 points are taken along s direction, 3 points in the t direction, resulting in total 3 times 3, 9 integration points. And the location of these points in each direction and the corresponding weights are same as those what we have studied for one dimensional case. And they are reproduced here. We have already looked at this earlier, except that the table starts from n is equal to 2, at n is equal to 1 integration point is 0, the location of integration point is 0 and weight is 2. So, here this table gives from n is equal to 2 to n is equal to 10. So, here in this portion of table the points and weights for n is equal to 2, 3, 4, 5 are shown. How to read this table? I already explained when we are looking at one dimensional case, and this portion of the table shows from n is equal to 6 to 8, and this portion of the table shows for 9 number of points and 10 number of points, Gauss points. As I mentioned, for n is equal to 1, x is equal to 0 and weight is equal to 2. So, now let us look at how to evaluate or how to get the coordinates for one by one integration. So, in s direction the location is at s is equal to 0, in the t direction the location is at t is equal to 0. So, the location of Gauss point is going to be 0 0, because in the s direction it is 0, in the t direction it is 0, and the weight in the s direction is 2, weight in the t direction is 2. So, total weight is going to be 2 times 2, 4. So, this is for 1 by 1 integration. Next, 2 by 2 integration. So, there are two integration points in s direction, two integration points in in the t direction. The coordinates of integration points in the s direction can be obtained from the table that we just looked at, taking number of significant digits as the accuracy that one is looking for. So, here the integration point coordinates in the s direction are shown, and also weight in the s direction at these 2 points is equal to 1. Similarly, integration point coordinates in the t direction are given, and weight in the t direction is at the 2 points is equal to 1. So, by combination of this, that is s is equal to plus or minus 0.577350269 and t is equal to plus or minus 0.577350269. By combination of these, we can obtain the coordinates of all integration points, and at each integration point weight is going to be weight in the s direction times weight in the t direction. So, that is how we can get weights and coordinates of all the 4 integration points. Similarly, 3 by 3 integration, from the table read out the coordinates of the integration points in the s direction and the corresponding weights. Similarly, same thing, or you can repeat for the t direction. If there are 3 points in the t direction as well, so same the coordinates of the integration points in s direction will be same as in the t direction. If one has different number of integration points in the t direction, then we need to read out the corresponding coordinates and weights from the table that is given earlier, and doing or calculating the weights as I explained, weight in the s direction times weight in the t direction, we get weights at all the points, and also by combining these coordinates in s direction and t direction, we can get the coordinates of all points in for this 2 dimensional integration. So, similar procedure can be extended for any order of integration. Now, let us take an example. Evaluate I is equal to double integral minus 1 to 1 minus 1 to 1 8 times s power 7 plus 7 times t power 6 ds dt using Gaussian quadrature. And let us start with 1 by 1 integration. So, in the s direction the coordinate is s is equal to 0, in the t direction coordinate is t is equal to 0, that is the location of integration point, and weight is weight in the s direction times weight in the t direction, which is weight in the s direction is 2, weight in the t direction is 2. So, total weight is 4, but the function value evaluated at s is equal to 0, t is equal to 0, that is integrand value evaluated at s is equal to 0, t is equal to 0 is it turns out to be 0. So, total integral is going to be 0 because the function value is 0, and whatever weight, that is even if you multiply with 4 we are going to get 0. And 2 by 2 integration, this is the integrand, and we need to evaluate this integrand at the 4 integration points where s and t values can be obtained from the table following the procedure that I explained. So, we need to evaluate this function value at these 4 integration points and multiply with corresponding weights and sum them up to get the integral, the approximate value of integral. So, all this can be, we can do this all these calculations in a table format. The calculations are summarized in the following table. First column shows point, second column shows what is the s coordinate of this point, particular point, and third column t coordinate of that particular point, and the fourth column shows the integrand value, that is f value evaluated at that particular point, substituting s and t values, and fifth column shows weight in the s direction, sixth column shows weight in the t direction, and seventh column shows weight in the s direction times weight in the t direction times the function value at that particular point. So summing up all the contribution from all the 4 points, that is summing up the values which are in the 7th column, we are going to get the value of integral. So this is using 2 by 2 integration, 2 points in the s direction, 2 points in the t direction. Similar procedure can be extended if one wants to use higher order integration, that is 3 by 3 integration, integrand or function, and calculations are summarized in the table. So 3 by 3 results in 9 integration points total. So the function value needs to be evaluated at all the 9 integration points multiplied with weight in the s direction times weight in the t direction, and the contribution from all the 9 integration points can be summed up to get the approximate value of integral, and the approximate value of integral is using 3 by 3 integration is 3.36, and whereas this integral, that is double integral minus 1 to 1 minus 1 to 1 8 times s power 7 plus 7 times t power 6 ds dt, we can also perform exact integration because this is integrand is very simple. S power 7 integral s power 7 ds is s power 8 divided by 8. Similarly, integral t power 6 dt is t power 7 divided by 7. So we can easily evaluate this integral value exactly and substitute the limits of integration, and if you do that, the exact integral can be evaluated or can be easily verified to be equal to 4. And if you see this integral in the s direction, we have highest power as 7, in the t direction highest power as 6, and we can as well apply the formula that we looked at when we are discussing one dimensional integral, that is n point Gaussian integration can integrate a function of order 2n minus 1 exactly. So we can use that thumb rule and we can easily back calculate how many points we can use in s direction and how many points we can use in the t direction. So 2n minus 1 is equal to 7 results in n is equal to 4, and 2n minus 1 is equal to 6 results in n is equal to 3.5, which needs to be rounded off to 4. So if one wants to evaluate this integral exactly, 4 by 4 integration needs to be adopted. So if one adopts 4 by 4 integration, then the approximate value of integral that we get by doing Gaussian quadrature matches exactly with exact value of integral, which is 4. So now let us take another example. Use 2 by 2 integration formula, that is total 6 points, to evaluate following integral: I double integral minus 1 to 1 minus 1 to 1 s square s t times t power 4 ds dt. So, the function is this one. As you can see here, the highest power of S is 2 and the highest power of T is 5. So, applying the 2n minus 1 rule that we have for deciding how many points we need to use in S direction and how many points we need to use in the T direction, 2n minus 1 is equal to 2 results in n is equal to 1.5, which can be rounded off to 2, and 2n minus 1 is equal to 5 results in n is equal to 3. So, we need to adopt 2 integration points in S direction and 3 integration points in the T direction to evaluate this integral exactly. So, that is what is asked to use, that is 2 by 2 integration formula. So, the approximate solution that we are going to get by adopting Gaussian integration is going to match with the exact results for this particular problem when we adopt 2 by 2 integration. So, all the calculations these are the locations of integration points. The details of calculations at each of these integration points and their locations and weights are given in the table. Total 6 integration points. First column shows the point integration point number, second column shows location in the S direction, third column location in the T direction, fourth column function value at that particular location substituting that particular corresponding S and T values, and fifth column shows weight in the S direction, sixth column weight in the T direction, and seventh column shows weight in the S direction times weight in the T direction times function value evaluated at that particular point, and summing up the function value or the total value of summing up all the values in the seventh column, we get the approximate value of this integral. You can see here the approximate value that is obtained using Gaussian quadrature matches very well with the exact solution for this particular problem. So, we have seen, so far we have seen as a part of this isoparametric quadrilateral element, we have seen how to derive shape functions for 4 to 9 node quadrilateral elements, and also we looked at isoparametric mapping concept for 2 dimensional elements, and also we looked at numerical integration for evaluating integrals over 2 dimensional domains. So, now we are ready to develop element equations by taking any one of the quadrilateral elements. So, now let us go and take the simplest element that we can have under quadrilateral element category, that is 4 node quadrilateral element. 4 node quadrilateral element for 2 dimensional boundary value problems. Using isoparametric mapping and the procedure used for triangular element, it is straightforward to develop finite element equations for any element. Equations for 4 node quadrilateral element for general 2 dimensional boundary value problem, we are going to develop the equations for 4 node quadrilateral element for general 2 dimensional boundary value problem. So, now let us go back and recall what is the differential equation for that we are using for general 2 dimensional boundary value problem. The differential equation is something like this, which we used when we are developing element equations using 3 node triangular element. So, now using Galerkin criteria for the problem gives us this equation basically Galerkin criteria is multiply given differential equation with the weight function. When we are using finite element method, shape function is same as weight function. So, integrate the given differential equation with shape function, and how many shape functions, it depends on what kind of element one is adopting. So, multiply given differential equation with shape function, integrate over the problem domain equated to 0, and this is the first step, and this equation needs to be further simplified. For that we use Green's theorem, and when we are looking 3 node linear triangular elements, I already gave you these formulas, integration by parts in 2 dimensions, double integral u times partial derivative of v with respect to x dA is equal to minus double integral over area v times partial derivative of u with respect to x plus line integral u times v x component of normal outward normal integrated over the boundary. Similarly, the second equation, these are the 2 equations that we get using Green's theorem, and we will be using these 2 formulas to simplify the previous equation further. Here an x and y are the direction cosines of boundary normal. So, using these 2 formulas and simplifying the previous equation, the first 2 terms of the previous equation can be simplified using Green's theorem formula that we just looked at, and that results in this. If you recall, we discussed in detail all this when we are dealing with 3 node triangular element, except that the only difference that you have between that and here is number of shape functions are 4 here, whereas earlier number of shape functions are 3, and the shape function expressions also are different for 4 node and 3 node element, except that this part is similar. As pointed out earlier, boundary integral needs to be evaluated over only the part of boundary on which natural boundary condition is specified. If you see the second part of the equation, integral needs to be performed only on S2. S2 is the part of the boundary on which natural boundary condition is specified, because the part of the boundary on which essential boundary condition is specified, we do not need to evaluate this integral, because it goes as a reaction term in the final equation, final equation system that we get. So, we ignored this explanation I have given you when we are looking at 3 node linear triangular element. So, now looking at the second integral, the integrand comes, the value of it can be further simplified, which comes from the prescribed natural boundary condition. So, from the natural boundary condition, the line integral, that is the boundary integral over S2, can be further simplified or further rewritten using this boundary condition, that is kx times partial derivative of t with respect to x times x component of normal plus ky times partial derivative of t with respect to y times y component of normal is equal to minus alpha t minus in brackets alpha t plus beta. So, substituting this quantity into this equation, it can be written like this, and now we need to make substitution of shape functions, shape function expressions. There are 4 shape functions, 4 shape functions for 4 node quadrilateral element. This shape functions needs to be in the parent coordinates, even though, or we will be mapping actual element onto a parent element. actual element is shown. Instead of performing calculations on the actual element, we are going to perform calculations on the parent element, and that is what isoparametric mapping is. So, the shape functions for 4 node parent element in terms of S and T can be put in a vector like this, and we can take the derivatives of these shape functions with respect to S and T. Derivatives of shape functions with respect to S and T, and vectors of nodal coordinates looking at the actual element, we can write the nodal coordinates here. There is a mistake. The vector of nodal coordinates consists of only x1, x2, x3, x4. Similarly, vector of nodal coordinates for y consists of only y1, y2, y3, y4. xy and y5 should not appear because we have only 5 nodes. So, using the nodal coordinates x1, x2, x3, x4, y1, y2, y3, y4, we can write isoparametric mapping relations which can be compactly written in a matrix and vector form like this. N transpose comprises of all the shape functions n1 to n4, and xn comprises of all the x coordinates of all the nodes x1 to x4. And once we have this relation, we can easily take derivatives, partial derivative of that x with respect to s and with respect to t. Similarly, y is equal to n transpose yn, again n transpose is vector of shape functions and yn is vector of y coordinate of all the nodes y1 to y4, y1, y2, y3, y4. Once we have that relation, we can easily take derivatives of y with respect to s and t. Once we have this partial derivative of x with respect to s, partial derivative of x with respect to t, partial derivative of y with respect to s, partial derivative of y with respect to t, we can easily calculate what is determinant of Jacobian. And derivatives with respect to x and y can be computed once we know the determinant of Jacobian. We can compute the derivatives of shape functions with respect to x and y once we know derivatives of shape function with respect to s and t, because if you see on the right hand side we have partial derivative of shape functions with respect to s and t, and that vector can easily be computed because shape functions are in terms of parent coordinates s and t, and this thus the x y derivatives of entire shape function vector can be written writing shape function derivatives with respect to x as a separate vector bx, b subscript x. We can write from the previous equation, we can write this relation, similarly by. And using parent element shape functions, trial solution and its derivative can be written like this. Trial solution can be written as n1 t1 plus n2 t2 plus n2 t3 plus n4 t4. in a matrix and vector form as n transpose d. Similarly, derivatives of t with respect to x can be written like this, b x transpose d. Derivatives of t with respect to y can be written as b y transpose d. So, we have the trial solution and also derivatives in terms of finite element shape functions. Now, we can substitute all this information into the equation. In this equation, thus substituting the trial solution into the Galerkin criteria and writing all 4 equations together in matrix form, we get 4 equations because there are 4 shape functions. So, substituting the derivatives of shape functions and shape functions, derivatives of trial solution and trial solution in terms of finite element shape functions and derivatives of shape function, we get this equation. And complete element equations can be written in standard form by defining following matrices. So, the previous equation can be rewritten in this manner: kx, ky, kp, k alpha, kx plus ky plus kp plus k alpha times d is equal to r cube plus r beta, which can be compactly written as kd equal to r. Here each of these matrices and vectors are defined like this. This is obtained from the previous equation. By comparing with previous equation, we can write this. And the integrals involved, you can easily notice that integrals involved in element equations are quite complicated and usually require numerical integration. So, that is the reason we looked at Gaussian integration in 2-dimensional case. So, in the next class we will be looking at the details how to evaluate all these area integrals and line integrals.